Hey folks, we're going to wrap up this unit on similarity by discussing proportions inside triangles. And that's our last lesson for the unit. Yay! I will be making multiple videos once again. See if I can cut this thing short, but gosh, I just talk so much. So we're going to discuss today proportions inside triangles. We're going to learn about something called the side splitter theorem. Then we're going to learn something about the side splitter corollary, and then a triangle angle bisector theorem. But most importantly, we're really going to hammer home proportionality. And that is the key element to the whole unit, is proportionality. So let's get started on this first video. We're going to discuss the side splitter theorem, which states that if Mr. Katz tells a joke, you must laugh so hard that your side splits. But no. The side splitter theorem talks about a line parallel to a side of a triangle. And remember, it doesn't matter which side, right? It doesn't matter which side. As long as it's parallel to a third side of the triangle, what happens? Intersects the other two sides and divides the sides proportionally. Okay, so it means it divides the sides proportionally. So the given proportion that's there looks at this. The given proportion looks at XR to RQ, right? And then that's going to equal YS to SQ. Okay, so we can look at it that way, but we can also look at a whole bunch of other things. This is what I want to make sure we understand. When you're looking at proportionality, remember in that first lesson we talked about equivalent proportions. So what this means, we can also look at it this way. XR to YS. We can look at it that way. XR to YS. And what would that be equal to? If I set this up with this, I would have to then look at RQ to SQ. I would have to look at it that way. That's another way of doing it. But wait, there's more. Okay, there's more. We could also look at, how about XR to XQ? What? We can do that as well. But what would that be equivalent to? YS to YQ. We could do that as well. All sorts of neat things that we can do to play around with this. You have to remember equivalent proportions. That is the key element. We can mess around with it all sorts of ways. And that is the side splitter. So if a line is parallel to a side of a triangle, we're going to have a lot of neat proportionality. Let's discuss some examples, shall we? Let's do it. So this is the side splitter theorem in action. I'll show you a bunch of different ways that we can do this. So the question is, what's the value of x in the diagram at the right? At the right, Mr. Katz, do you know your directions? Yes, I do. I know it's below. Anyhow, copy and paste. So finding the value of x. We have a lot of things that we can do with this, with the fact that we know that this is parallel. Okay, we definitely have side splitter in action. We could set up a whole bunch of proportions. We could look at x plus 1 to x. We could look at it that way. And if we look at x plus 1 to x, we could look at 12 to 9. We could look at it that way. We could look at x plus 1 to 12. Okay, so we can look at it that way. If we looked at x plus 1 to 12, we would have to look at x to 9. We could look at it that way. We could look at the whole thing, right? We could look at x to this whole side, right? What would this whole side be? Anyone know? Anyone know? Raise your hand. Okay, good. X plus 9, that's correct. All right, so we can do x to the entire side, and that could be equal to x plus 1 to this whole side. And what would be the measure of this whole side? That's right. Raise your hand. Good, good. X plus 13. Very good. X plus 1 plus 12, right? So we could set this up in a whole bunch of different ways, and then we have all of our proportions that we could solve. All of these are going to be the same thing. I will show you this one. It is awesome sauce. Okay. So you pick your proportion, which way do you want to see it, and then use your cross product property, right? The product of the extremes is equal to the product of the means. So how about I'll work on the first one I noticed, x plus 1 to x. So let's consider that, okay? So we're going to compare x plus 1 to x. That would be equal to 12 to 9. And now what we do is use cross products, okay? The product of the extremes, x plus 1 and 9. And remember, when you multiply, make sure we use the distributive property. So that would be 9x plus 9. if you ask me how, I'm going to ask you to show your work, because the work you want to show is this, right? Oh yeah. Distributive property, right? 9 times x plus 1. And then the product of the extremes is equal to the product of the means, right? X times 12, which is 12x. And so we have our equation set up this way, and now I should remember the x, and now we could easily solve for x. So we subtract 9x on both sides. 9 would equal 3x, therefore x equals 3. So we can find the value of x that way. I do want to show you this one. But we could do the same thing with this proportion, right? 9x plus 9 equals 12x. What? 9x plus 9 equals 12x. All right, so look at how they're the same. 9x plus 9, 12x. 9x plus 9, 12x, right? It could happen either way. But then you ask, all right, Mr. Katz, what about this crazy thing here? The product of the extremes. So we have x times x plus 13 is equal to the product of the means, x plus 9 times x plus 1. Now, you guys haven't heard me teach algebra so much in my geometry course, but let's see how this works. So on the left-hand side, we have the distributive property. X times x is x squared. X times 13 is 13x. We know that. But what do we do with this? Right? The distributive property, or what you guys probably have learned, FOIL. I don't call it FOIL, but I just use the distributive property in my head. X times x is x squared. X times 1 is x. 9 times x is 9x. And 9 times 1 is 9. Okay? Or, like I've said, you probably have learned FOIL, first outside and inside last. But it's the distributive property. So let's do some simplification. The left-hand side is x squared plus 13x. The right-hand side, I have x squared plus x plus 9x. That's plus 10x, and then plus 9, right? So what do we do here? Well, let's gather our stuff together. We've simplified both sides, but we have an x squared on each side. So what can we do? Let's subtract x squared from both sides. Boom, boom. What will that leave us with? Okay. On the left-hand side, 13x. On the right-hand side, look what happens. X squared minus x squared, see ya! And then we have 10x plus 9. Okay, all right, fair enough. What now? Now we're going to do our old separation stuff, undo, subtract 10x from both sides. And then what will we have left? 3x equals 9. 3x equals 9. Yes, yes. Oh my God, that's amazing! So x equals 3 no matter how you do it. So this is the beauty of not just the side splitter theorem, but of all proportionality. As long as you have equivalent proportions, it doesn't matter how you see it as long as you're seeing it correctly. So when you look at your diagram and you see proportionality, you must see it correctly. You make sure you're comparing apples to apples, oranges to oranges. Okay, so we have to be very careful with how we do it. So let's do one more example. We'll call it a day for the side splitter, and then we'll come back in another video for other fun stuff. So here's another example. What is the value of A in the diagram below? So it doesn't matter how you see this, as long as you're seeing it correctly. We have our parallel lines, true. What are some of the proportions that we could see? We could see A to A plus 4. We could see that. There's nothing wrong with that. But what would that be equal to? 12 to 18. All right, that'll work. We could see A to 12. Okay. What would that be equal to? A plus 4 to 18. Now, are these two the same? Yes, as a matter of fact, they are. Because look what's happening either way. The product of the extremes, 18a. The product of the extremes, 18a. The product of the means, 12a plus 48. 12a plus 48. So it doesn't matter how you see it, it can still be the same. And can we do the entire side as well? Yes, we can. A to 2a plus 4, 12 to 30, right? We could do that as well. So it doesn't matter how we look at it. Either way, we're going to have the product of the means, no matter how we look at it, is going to be, or excuse me, the product of the extremes is going to be 18a, and then the product of the means. Interruption. 12a plus 48. So it doesn't matter how you see the proportion, as long as it's equivalent. And now we have our equation to solve. And so let's solve our equation. We subtract 12a from both sides. Hopefully by now you see the solution. So 6a would be 48 Divide both sides by 6. A equals 8. Bam, bam. And that's the side splitter theorem in action. So come back later for another theorem, and we'll talk about the corollary to it. And I will see you later.